Okay. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, June 25, 2021. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a rain-swept evening in Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. Today, we are joined by members of the Rockport Cultural Council, Gloucester Area Astronomy Club, and other curious folk. Thank you for coming. This evening, I will be talking about our cosmic origins, a wide-ranging topic involving both the Earth and space sciences. Just consider the origins of basic elements, such as the gold in my wedding band or the silver in my friendship band, or simple molecules such as the water in my glass, ta-da, or minerals such as the blue quartz found here on Cape Ann, beautiful blue quartz, or composite rocks such as the granite that characterizes most of Cape Ann, where I live, or plant life, such as the ash tree that got cut down to make this log, or squishy animal life, such as you and me. There is a lot to cover, so let's get to it. Okay, so I'm going to share my screen. And get to the PowerPoint and slideshow, the beginning. Okay, so as I noted, I'm talking about our cosmic origins, and that can involve all kinds of origins. And there's a timeline for these origins. I have to get some people in, admit all. Okay. All right. Okay, and here there's 8 stages from the particulate to the cultural and our future, but I'll probably get as far as the biological in exploring our cosmic origins. Okay. Go back. Okay, there you go. All right. So a question all of us can ask is, how did our earthly home come into being? Now, not all of you live where I live, but I have an example which I'm going to focus on. You will have your own examples, which are shared in many ways, especially as you go back in time. But I live on Cape Ann, which is a part of Massachusetts. Some of you might recognize Boston and Cape Cod, the other Cape. I am a chauvinist for Cape Ann, and it's surrounded on 3 sides by ocean, which is a very important aspect of our planet. And a big question is, how did this rock, which is separated from the mainland by 2 road bridges for cars and 1 railroad bridge, how did this rock get made? Okay. So the answer was provided by Carl Sagan rather nicely, saying that if you wish to make an apple pie from scratch, you must first invent the universe. And so we're going to take that approach to discuss how all this got made, including myself, who lives right around here where my arrow is shown. Okay. So you have to go back to the first light, the hot Big Bang, approximately 14 billion years ago. Some people say 13.7 billion years ago. Other people say 13.8 billion years ago. And that's when our space and time began. And it was shortly followed by an epoch of inflation in the first 10 to the minus 32 seconds, when the universe expanded. It doubled in size approximately 60 times in less than 10 to the minus 32 seconds. And that flattened out the universe, got rid of any curvature it might have had, and solved other problems in cosmology. And what you have is basically a bitch's brew of particles, including electrons, protons, neutrons, and photons. Those are the particles of light. Now, there was a period over about 3 minutes or so when the protons and the neutrons could combine to produce nuclei of helium. So that would involve 2 protons and 2 neutrons. It had to occur within about 5 minutes or so because the neutron tends to decay back into its constituent protons and electrons and neutrinos. So we know that this nucleosynthesis, this basic nucleosynthesis, probably happened in the first 3 minutes or so. Another 380,000 years would have to pass before the universe expanded enough to cool enough and so enable the electrons to recombine back onto these nuclei, either the hydrogen nuclei or the helium nuclei. And that was when you first had neutral atoms as opposed to free charges. And that enabled the light to escape. No longer did the light get harassed by pesky charges, and it could stream out and be seen as the cosmic microwave background. So that's really the first light that we see, this epoch, which I'll show later on. Then there's this dark age, which we know very little about. Our instruments aren't powerful enough yet, but they're getting there. And that's when there was more cooling and congealing and maybe the first galaxies. We now think that the very first stars and galaxies formed sometime around 300 million years after the hot Big Bang. In fact, there's a recent galaxy detection that confirms this. These galaxies were not the galaxies that we know today. They were little blobs which merged to form the giant galaxies that characterizes the universe today. Okay, so it's a long, strange trip, a tall tale, but the observational cosmologists and the theoretical cosmologists do seem to be converging on this scenario. So here is the first evidence that we have, the first hints of structure in the cosmic microwave background. This is an all-sky picture of the cosmic microwave background. This is after they had to remove the foreground of radio emission from the Milky Way itself. And so this is what's left over after they've gotten rid of that and other foregrounds. And it's incredibly smooth, actually. They've enhanced the contrast, but it would be the equivalent smoothness as a well-groomed ice skating rink, the surface of a well-groomed ice skating rink. So there's the contrast, the over-densities and the under-densities are basically 1 part in 100,000 or so. And the spacing is characteristic of about a 1 degree spacing, which is consistent with a universe which doesn't have curvature. Okay, so if you had an enormous house, bigger than a galaxy cluster, it would still look like a cubic house. It wouldn't look like it was curved. And that's because the space it's in is not curved either. So they've learned a lot about the universe just based on the characteristics of this cosmic microwave background. Come on. There we go. Okay. So what was in the universe back then? Well, it was different. It consisted mostly of dark matter, which we don't know much about. We know that it's probably not ordinary stuff, ordinary dark matter like dead stars or planets. It's probably some strange particles, but that's about all we know. And then, of course, the universe was ablaze with photons of light, and it did have ordinary matter in the form of atoms and a good amount of neutrinos, which is a form of dark matter. It's kind of hot dark matter. And so that's basically what the universe was made of back then. It's different now. You still have a lot of dark matter, along with the ordinary atoms that we're more familiar with. But now there's all this dark energy, 72% dark energy, which we know even less about than we know about the dark matter. We're fairly persuaded in favor of the existence of this dark matter because there must be something that is propelling the universe of galaxies to be expanding ever faster. So that's one reason for the dark energy. Also, another reason for the dark energy is the flatness of the universe. As I said, it doesn't seem to have any strange curvature, and something must be flattening the universe in addition to all the matter energy that we can detect. So it's strange no matter when you look. If we look deeply with our most sensitive optical telescopes, such as the Hubble Space Telescope, with the longest exposures to make the Hubble Ultra Deep Field and other deep fields, they see galaxies upon galaxies. Some of these are nearby and they look like giant galaxies similar to the Milky Way galaxy, but then there are a lot of little lumps and bumps that can be seen in these green squares, and if they're blown up here, and you basically see, you know, little lumps, little bumps, what I am fond of saying, little red turds at the edge of infinity. And they don't look like today's galaxies. We are biased towards their regions of active star formation, but even so, they do seem to be much smaller than the ones that the galaxies that we're familiar with today. So how do you get the bigger galaxies? Well, there's a lot of merging. The universe was a lot more crowded back then. And so the likelihood of galaxy or subgalactic mergers into bigger galaxies was much greater. And if there was any residual rotation to the merger process, you would end up getting a net rotation to the system. And if that condition exists, you will end up getting a preferential collapse towards the midplane, basically perpendicular to the axis of rotation. And that's how we think galaxies like our own galaxy are made. You end up getting maybe a bulge-dominated system, but with a flattened disk in ordered rotation. How long it takes, we're not sure how long this process takes, but we keep finding galaxies at high redshifts, implying great look-back times corresponding to only 300 million years after the Hot Big Bang. The universe was able to get itself this much together. So our own Milky Way looks something like this. This is an artist's depiction of our Milky Way galaxy. In this depiction, we have a central bulge made up of yellowish stars like the sun, so they're essentially relatively low mass and probably relatively old. There's a central bar of these sorts of stars as well. And then going off of the bar, there's these two spiral arms. There's two major spiral arms. The cord is out as to whether there's two spiral arms or four spiral arms, but we're pretty convinced that there are at least two spiral arms. And you might notice that the spiral arms contain blue stars, a bluish light, and that's because there is a skim coat of blue, hot, relatively young stars because they burn, these hot blue stars burn brightly and they don't last as long. And so if you see them, they must have been recently made. In addition, there are these little red zones, and those indicate the places where the most recent star formation has been taking place because there's still gas to respond to the newborn, young, hot stars. Okay. looking edge on our galaxy, you can sort of see what our galaxy looks like just by looking at it edge on. But this is an example, another example of a galaxy, NGC 891, and it shows that the disk is pretty thin. It has blue stars in there, but also an awful lot of obscuring dust. And this dust is basically tracing clouds of gas and dust, and it's the dust that's obscuring the light from behind. And this is important because this is where star formation is occurring today. If I was a betting man, and I guess I am, I play poker, I would say that this galaxy, Messier 109, comes closest to what our Milky Way galaxy looks like. This is an actual picture, and it has the central bulge, a bar of yellowish stars. The spiral arms hang off of the bar. They're bluish, along with the gaseous regions. Which I would regard as the crucibles of creation, still occurring here in this galaxy. So I've made a big deal about galaxies. You had to make them first, and but the question is, what do galaxies have to do with the origin and evolution of Earth, my Cape Ann home, and your homes? And I've said this before, I'll say it again, that just as it takes a village to raise a child, so too it takes a galaxy to bring forth stars in the galaxies and the chemical complexity that is necessary to make rocky planets and life on these worlds. And so going back to what you can see, here is a view of from a desert mountain in Chile, the Cerro Tololo Inter-American Observatory. And you can see first this object, it's a naked eye object. You can see in a dark sky like this. This is the Large Magellanic Cloud. It's a companion galaxy to our Milky Way galaxy. It's about 1/10 the size of our Milky Way galaxy. And here's the Small Magellanic Cloud, another companion galaxy in the thrall of our galaxy. This has been said to look like a pork chop. I don't know, maybe so. Our Milky Way galaxy, or a part of it, is seen here. And there's some prominent members here. I think the brighter object here is Alpha Centauri system. It's the closest stellar system to us, only 4 light years away, or 4.4 light years away. There's Beta Centauri, which is farther away. And then there's this beautiful kite-like asterism of stars, which is called the Southern Cross, or Crux. And this can be seen in the flags of Brazil, New Zealand, Australia, very popular pattern in the sky. And then on top of it, or above it, is the coal sack, which is a relatively nearby example of a gas cloud whose associated dust is obscuring light from behind. So there's also more evidence of obscuring dust here. And we can see that all along the Milky Way. As is evident with this all sky view by Axel Mellinger, how did he put it together? Well, he took pictures from the northern hemisphere, and he took pictures from the southern hemisphere, here's the Magellanic Clouds, and he stitched them together to make this wonderful mosaic, all sky mosaic. And you can see there's a lot going on. And there is what seems to be a direction, a favored direction towards Sagittarius, and that is the direction of our bulge, a galactic bulge. And there's regions of redness, and those are where these crucibles of creation or galactic ecosystems are very active. But I'm going to focus on this one particular region here. This is the Orion star forming region, seen in the visible. And I'm going to now focus in on that. Most of you are familiar with Orion as a constellation. It's available to everybody on the planet because it straddles the celestial equator. So even the folks in the south can see Orion, though Orion might look upside down. Here's the head, Maisa of Orion. This is one of the shoulders, Betelgeuse. This is a ruddy colored star, supergiant star, which was a star, literally was news item in February, back in February, January, February, when it dimmed strangely, but it's now come back to its normal brightness, quote unquote normal brightness. It's a variable star. And then there's Rigel, which is a bluish star near the knee of Orion, and the belt stars. That's what's most prominent for people looking and trying to find this constellation, is this straight line of three stars: Alnitak, Alnilam, and Mintaka. And then, so I'll be talking about a star forming region right here. That's the Horsehead Nebula region, and then I'll be talking further about the Orion Nebula further down in the Sword of Orion. So if you looked with different kinds of eyes, far infrared eyes, this same scene would look like this. And it's very different. In fact, it's so different as to be bedazzling, very difficult to comprehend. But this is the light from dust that has been warmed by the stars. So the Maisa, I think it's a star system, system of two very hot, bright stars, which have basically heated up a region of gas and caused it to expand, and you end up getting a shell of dust in the outer parts, which has been warmed by those stars. So that's one thing. The Horsehead Nebula region is here, and the Orion Nebula is here. This is the plane of the Milky Way galaxy. Orion kind of hangs off of it a little bit because it's relatively nearby. In fact, it's the nearest site of burgeoning star formation to us, especially the Orion Nebula region. Okay. Here is the view of the Horsehead Nebula region, and you see, basically, you're seeing a cloud of molecular gas and dust, and at these mid-infrared wavelengths, you're actually detecting the glowing dust and a particular kind of molecule known as a polycyclic aromatic hydrocarbon, PA. But there is this protuberance sticking up, some resistant region of gas and dust, which is resisting what's happening to this whole surface here. It's being eroded by the photons, the ultraviolet photons coming from a star around here. It's called Sigma Orionis, and it's a very hot star, produces lots of ultraviolet radiation, which is blasting into this molecular cloud and ripping the molecules apart, and then ripping the electrons off of the atoms. So that's what it looks like in the mid-infrared. Here's actually a better picture with the Spitzer Space Telescope, centered. Basically, it's showing the light specifically from the polycyclic aromatic hydrocarbons. So already we're seeing some fascinating chemistry in these galactic ecosystems. In the visible, this is what most people would recognize as the Horsehead Nebula, and it highlights the cloud of gas and obscuring dust grains. But what is this pink light? Well, as I said, there's this star off to the right-hand side, which is hitting gas associated with the cloud and causing the molecular gas to go atomic and then to rip the electrons off. And the hydrogen produces this fascinating glow when the electrons recombine back onto the hydrogen nuclei, the protons. And so it makes a great background to see this object in silhouette. In the near infrared, courtesy of the Hubble Space Telescope, you can actually see some of the stars which are being born inside this globule, is what they call it. And this star obviously is doing something there. I think that might be a jet, though it could be a galaxy far, far, far away. But people have worked to see which stars are actually in the nebula and not background objects or foreground objects. So this is an example of a star nursery. Going further down towards the Orion Nebula area, one finds recently, this is recent data, a molecular cloud in the form of a filament. And this is being seen in the emission from ammonia gas. So what is that, NH3 or NH4? I always get that wrong. It shows just how filamentary the star-forming molecular gas is. And overlaying on this, in this image, is a bubble of star-warm dust emitting in the infrared, courtesy of the WISE infrared space telescope. So pretty good stuff. So remember this bubble, because I'm going to show you another view of it. It's a view of the bubble from the Stratospheric Observatory for Infrared Astronomy. This is the 747 jet that gets above 99% of the Earth's water vapor, and that enables them to see at these wavelengths. And they're looking in the light, far infrared light of ionized carbon. And because carbon emits at a very specific wavelength, they can track the wavelength as observed, and so infer from the Doppler shift the velocities. And they've inferred that this is an expanding bubble, and that it's probably being made to expand by strong winds from the stars being born in here. So everything is moving, everything is changing in these cauldrons. At another wavelength, in the near infrared, you can actually see the cluster of stars that's being born inside this molecular cloud, filamentary molecular cloud. And there's about 1,000 stars, and it's centrally concentrated. And this one's an interesting region. This is a star that probably has a pre-planetary disk, and the star is blowing a wind out both ends of the disk. The other, I guess that's about all I want to note here. So it's a robust cluster of stars, and this is a very new object. It's only a few million years old, 1 or 2 million years old. The first hominids on this planet did not see this object in the sky, which was known as a smoking star to the First Nations. The Hubble Space Telescope going in the visible allows you to see the gas, which is being what was once a cold molecular gas system, now is been turned into a plasma of ionized hydrogen, which is seen in the red here, ionized sulfur, seen with a little more yellow here, and there's also ionized oxygen near the center. And so you're basically seeing a blister on the near surface of a molecular cloud erupting, or you could think of it almost like a volcano. But there's a huge cavitation in what was once a dense region of gas. Looking even closer, you can see that there's a shock front here. This is a photoionization front, which is basically a UV light coming and hitting this area hard with ultraviolet photons. Here's a jet from an embedded newborn star. And then, of course, the center here, you're starting to see the brightest stars in the cluster. And we'll home in on that. And here they are. They're known as the trapezium. They're easy targets for amateur astronomers with small telescopes. And you can see there are strange things going on, especially around this star, Theta 1 Orionis C. And you can see that there are what look like young stellar objects. They kind of look like those poor unfortunate souls in The Little Mermaid, and because you have these cometary systems, the stuff that's getting blasted. There's also shock waves in front of some of them, and I'm going to go even closer and just look at these individual objects, and you can see, in addition to the shock waves and the tails, some of them have what look like preplanetary disks, protoplanetary disks, seen edge on here. This one's seen edge on with a central protostar here, and then this one is seen face on with a central protostar. Pretty neat stuff. You can actually see planets in formation, or at least the disks that will turn into planets in a few millions to tens of millions of years. And so here is a simulation which pretty much gets you there. Let's see if I can, oops, go back. I want to be able to, I can hit it. Okay, good. So here is the simulation, I hope. And, oops.
That face that is usually covered by her phone has finally made an appearance. That face wouldn't be doing
wait for
that
this
if you
to
weren't
go.
staying
Skip
at a
that. There you go.
House.
Okay, here we go. So you're seeing gravity at work here. Any over densities and under densities get amplified into tendrils of unstable gas that can lead to stars, and then those stars and the disks surrounding them combine to produce jets, which have an effect on the whole system. And the net result is kind of a filamentary system of newborn stars. Set to lovely music. I think we're almost done. So I'm going to stop it here and get back to where we were. There we go. Okay, good, good. That worked out. Yay. Fair amount of chaos leading to associated regions of newborn stars. Concentrating on just one of these protostellar cloud cores, there might be a sequence such as is shown here. You have the cloud core, and then that leads to a protostar with a disk of material surrounding. And that disk serves as an accretor, kind of a way for new material to stream into the protostar. Well, the protostar announces its displeasure by shooting off jets in opposite directions. And we can see all these stages at various wavelengths. And the jets, the winds combined to sweep out the preplanetary disk, so that what's left over is just a mature planetary system, just planets. Much of the debris, the gas and dust is blown out. And this probably takes millions to tens of millions of years for the solar system. It probably took around 10 million years. So that's all without even thinking about what the massive stars do. And I want to draw your attention to what one of these violent regions can do. This is the Eagle Nebula, M16, at visible wavelengths. This is the head of the eagle, I believe, and this is the wings of the eagle. And the stars here, somewhat obscured by the head of the eagle, the hot stars, have cavitated this whole region. What was once probably a dense molecular region has been cavitated by the starlight and the winds, with the exception of these three pillars, this pillar, and this pillar. And these are resistant globules of remnant molecular gas and dust, which are denser and so harder to photo erode. And you can take a closer look at these things. These are the iconic images of the pillars of creation, so-called pillars of creation. Kind of looks like a coral reef underneath the hot sun. And where the action is where the starlight is impinging on these surfaces and photo eroding the material. And if you look even more carefully and with a close-up, thanks to the Hubble Space Telescope, you can see that there are these evaporating gaseous globules or eggs. And what you're seeing is basically a race between these globules forming a stellar and planetary system, and or being eroded away. And it's not clear who is winning. So a lot of dynamics. Other areas show a little bit of humor. There is an intense star forming region in the constellation of Carina in the south. And a part of this region includes this globule, again being photo eroded by a star somewhere over here. And I like to call that the Flippin' Bird Nebula. But my poster child for these crucibles of creation has to be NGC 3603, also in the constellation of Carina. Not only does it have a centrally condensed cluster of hot, bright stars, which are best seen in this image. There's probably a lot of lower mass, cooler stars as well, but this one brings out the hot stars. There's even a star that's blowing its top. And then there are these pillars, once again, pretty huge pillars of resistant material with all sorts of photo erosion and other kinds of ultraviolet processing taking place at these surfaces here. Some of the processing has chemical associations. So the UV can rip up molecules and put them back together in a process known as photolysis. So there's some interesting astrochemistry taking place here as well. And speaking of astrochemistry, I've been talking almost all about the formation of stars, but the subsequent evolution and deaths of stars also adds to the cosmochemical mix. And examples of these are with these so-called planetary nebulae, such as the Ant Nebula. And so you take a star like the sun, it's lived out its life, say, and then it turns into a red giant. It stops fusing hydrogen in the core, starts fusing it in the shell. It becomes a red giant, and it expands and starts losing control of its outer atmosphere. The outer atmosphere ends up being cooler and cool enough for some of the gases to crystallize. And so you can get the first grains of interstellar dust manufactured in the outer atmospheres of these red giant stars. Silicates like
I'm sorry, dear. I'm under the headphones.
Okay, silicates such as what made that blue quartz that I showed, and then graphites as well, and they're all ice coated, and then they get blown out in a later stage of the star's evolution where it really loses control of its outer atmosphere, becomes unstable, and starts producing strong winds, which in this case look very asymmetric. And then that material gets illuminated by the hot remnant core of the star, and they end up glowing in a fluorescent process. as a result of being hit by those ultraviolet photons. So we see these as beautiful objects, and we're basically seeing astrochemistry in progress. A good example of this is the Ring Nebula. This is an attractive object for amateur astronomers. We can see this area, the ring, but in the infrared, courtesy of the Spitzer Space Telescope, they see this roseate, like a carnation of dust that has been blown out in prior episodes as the star was evolving towards its death. And the dust is being warmed and it's made to glow, and we can see it in the infrared. All this stuff gets blown out and will intermix with whatever molecular cloud material is in the galaxy. I can't resist showing this rogues gallery of planetary nebulae. These are some of the most beautiful objects in the sky, and they're observed beautifully with the Hubble Space Telescope. Many of them are asymmetric in different ways, with bipolar structures, and then with rings, etc. How this all gets formed is still a major area of research. They know that there must be some sort of structure down near the central star area, which is causing certain directions to be favored in the outflow. One way is to have a planetary system around the evolved stellar remnant, and that could be throttling the outflows. It could be a second star that is causing the material to flow out in an asymmetric manner. Okay. Up the masses, and you end up getting more violent outflows. This is the luminous blue variable star Eta Carina with a nebula.
My temptation is to slam the door, but you don't have to anymore. Just the light pool of
There you go. Sorry. And this object was the second brightest star in the sky, I think in 1840. But what we see today are these two bubbles, bipolar bubbles, blowing outward. And there's going to be all sorts of material that was cooked up in the massive star that's now flowing outward and will mix with the interstellar medium. And this gets even more pronounced with stars that literally blow up. Eta Carina has yet to blow up as a supernova. It could, but we do have evidence of stars blowing up. The Chinese and the First Nations, the Anasazi Indians, recorded a daytime star in the constellation of Taurus in the year 1054 AD. And what we see today is basically this beautiful nebula. This is the guts of the star that have been blown out by the explosion. And we're seeing very hot gas, million-degree gas in this X-ray coated blue. The visible, which is tens of thousands of degrees, is coated green here, and the infrared, which traces warm dust, shock dust, which is coated red here. And so this is all stuff that was once inside the star and has now been blown out. And in that demolition, heavy elements such as the gold in my ring, which the gold in my ring and the silver in my ring may have been formed. There's another contender of merging neutron stars might also produce these sorts of things. Again, it's massive stars and their evolution, which is producing heavier elements to mix in with the interstellar broth. One of the most recent supernova remnants is Cassiopeia A, and you can see it's a very busy affair with the material coated blue in X-rays, so that's the million-degree gas. The green stuff is coated to represent tens of thousands of degree gas, and that's in the visible. And then the red is the dust, corresponding to what can be seen in the infrared. And the neutron star here, I believe, is this. I'm not sure. It could be that one, the remnant. All this is going out and will add to the mix. Supernova remnants don't last long, around 50,000 years. They have lifetimes similar to that of volcanic features here on Earth. They dissipate into the interstellar medium. This is actually not the guts of the star, but actually material that has been piled up by the shock wave from the supernova. And this is a very popular object for amateur astronomers to observe here in the Northern Hemisphere. So all this creative commotion has been going on for the 12 billion year history of our galaxy, which has allowed the galaxy to become a breeder of chemical complexity, and also a breeder of new worlds, including our own planet Earth. And the places where it's happening most recently are these red objects, where the gas has been ionized by ultraviolet photons from the hottest stars. So the Milky Way is still actively breeding more chemical complexity and new worlds. Some examples here, just a few, are these stellar nurseries in Sagittarius. Can be seen with binoculars in the summertime, including the Lagoon Nebula and the Trifid Nebula. Again, that red glow is due to the once cold molecular hydrogen having been ripped apart into atoms, and the atoms, electrons having been ripped off and then recombined. Focusing on the Trifid Nebula, you see a pink area and a blue area. That pink area is from the hydrogen, which is fluorescing. The blue area is basically it's basically what you see with the blue sky. It's gas, which is scattering, gas and dust, mostly gas, scattering light from the stars. But this image, which is not in the visible, shows something completely different. It's in the mid-infrared, and the color code tells me here that I'm looking at the molecules, the polycyclic aromatic hydrocarbons. These are mats of benzene rings, or benzene rings arranged in a mat. The interior here is the dust, which is being warmed by the starlight within. And here are two versions of the same thing. There's these are the molecules, and this is the dust. A better version in its entirety is this, color-coded with the polycyclic aromatic hydrocarbons here, and then the dust here. Pretty neat. So even at these large scales of, several tens of light years, there's fascinating molecular stuff going on. And looking out, zooming out, you'll find that most of this activity is happening in spiral arms. This is an artist's depiction. And we are in the Orion arm, or spur, sometimes they call it. Some of these nebulae are in the Sagittarius arm, so we're looking towards the center of the galaxy in this direction, much farther away. So that's another arm, and looking in the opposite direction, you would see objects like the Rosette and the Crab Nebula in the Perseus arm. So the spiral arms have something to do with it, to get all this material swept up and gravitationally unstable to collapsing and forming things. Going closer, within 200 light years of the sun, you can see just a mix of stars. And there are some that some of us might know, such as Aldebaran and Arcturus and Vega. But there are other stars which you might know, might not recognize. And in general, there is no pattern in the stars, because we're just basically in amongst an ambient medium of stars of varying birth dates. So That's not characteristic of the spiral arm. And looking even closer, yes, we see that the Sun and Alpha Centauri and Procyon and Sirius are relatively bright compared to the other stars in the solar neighborhood within 10 light years. We basically are dominated by these little dim red bulbs. That's what dominate, and they might have formed long time ago because they last so long. But the brighter stars like the Sun and Alpha Centauri, they might be more recent objects. And in fact, we have evidence to think that the Sun and solar system was created 4.6 billion years ago. We have meteorites that have impacted Earth, and we can date them with radioisotopic methods. And you hit a max of around 4.6 billion years. So they were probably from asteroids. And so that's the date of those asteroids. Also, what other evidence? Oh yeah, the moon. The moon has rocks which have been brought back by our astronauts, and we date them to a maximum of about 4.6 billion years ago. That's 7 billion years after the Milky Way was formed itself. It was formed 12 billion years ago. We're pretty confident. And so what that means is that we have been the beneficiary of thousands of generations of massive stars that have come and gone and contributed their largesse to the overall chemistry of the galaxy. And in fact, were we born early on in the history of the Milky Way galaxy, we might not have been able to have the rocky planets that we have today, Mercury, Venus, Earth, and Mars, because that stuff hadn't been cooked up yet. But we do. We have a rocky planet composed mostly of silicates, silicon and oxygen, and it's covered in water, and it's been moist. That surface has been moist pretty much throughout the life of the Earth, which makes it unique among all the other planets. There's water on and in Mars, but it's pretty much frozen. And who knows, there might have been water on Venus back in the day. We beginning to suspect that there was a period where Venus did have water, but basically Earth has had water throughout much of its life. And in addition to the water, there's land, and that land has been growing. There was more water than land, but nowadays there's significant amounts of land, and it has been transforming its surface topography courtesy of the plate tectonics that move the crust around. And so I get a kick out of this, where Billy says, "The ranger said the river dug the canyon, Mommy, and you said God did it. Who's right?" Well, it begs a rather philosophical question, but I have to say that the geologists have put together a pretty good mechanism by which these transformations can be understood. And that is the rock cycle. We can start with the magma below the surface of rock, hot, molten or semi-molten rock, which rises and cools to form igneous rocks such as the granite on Cape Ann. And if there's further uplift due to mountain building, you end up getting these things that stick up and get worn down. There's weathering and erosion, and all those sediments settle down into deposits, which get buried and lithified, which means baked into rock. And you end up getting sedimentary rock, such as sand into sandstone, mud into shale, and life, calcareous life forms, like seashells, into limestone. That is a form of deposition. There's other ways to get limestone as well, I have to admit. But then if you get further heat and pressure due to mountain buildings, say, you will get recrystallization to make another type of rock. The sandstone turns into quartzite. The shale turns into slate. The limestone turns into marble. And all this eventually can get subducted or buried back down along a subduction zone due to the motion of the plates, the continental plates, and this stuff ends up going back down into a magma state, and the cycle continues. So this has been a rather successful model, and I'm impressed. So here's the timeline that has been put together for Earth's history. And you have the formation of Earth 4.56 billion years ago. There was it differentiated. What that means is that the heavies settled to the center and the lights floated to the top. So you have iron and nickel core in the center, and you have silicates in between, and the lighter silicates in the crust. So that happened pretty early on. There was an impact around 4.5 billion years ago, where a Mars-sized object is thought to have hit the Earth to produce the moon. And ever since then, the moon and the Earth have been a duo, a dynamic duo. The oldest crystallization seems to have occurred around 4.4 billion years ago, so the Earth started cooling back then. But there were still lots of impacts because of the protoplanetary disk was full of stuff, and there were a lot of impacts, and so it's not clear when the Earth itself was able to really cool enough to harden up, to have a crust that's thoroughly hardened. It might have been around 4 billion years ago where they had the oldest rock. The first evidence for life is isotopic 3.8 billion years ago. It's the ratios of various isotopes such as carbon, which suggests that life was kicking in. But the first fossil evidence is around 3.5 billion years ago. And you're just talking about simple microbes. Here is a picture of the simple microbes in a colony, but they do have definite evidence for it around 3.5 billion years ago. And so that was microbes, photosynthesizing. Some of them were photosynthesizing. We have evidence for that with the stromatolites that can be found in the shallows of, say, Australia. And then around 2 billion years ago, there was enough photosynthesis to jack up the content of oxygen in the atmosphere. That was bad news for most of these microbes, but good news for a small minority of them that could handle this injection of this this gas rather than being a poison. It was good for these microbes, and that led to the formation of microbes with nuclei in their cells, where all the DNA and RNA could reside. And these are known as eukaryotes, and that's what's led to the complex life forms that we know today, leading up to around 600 million years ago, trilobites and other very fascinating life forms that we see in the fossil record. The dinosaurs come around 200 million years ago, and then of course we humans are only in the very recent million or so years, the hominids. So that's the timeline. I like this particular rendering of the timeline because it combines both geology and life. You start with the Cambrian explosion of life forms in the fossil record 550 million years ago. And then there's all this motion of continents, which I'll show, and an ocean, which was important to my own Cape Ann, and various mountain building events in the North American continent, and the Permian, where the extinction around 245 million years ago nearly wiped out all life on Earth. And that laid things open, maybe opened up a niche for the dinosaurs to prevail. And they prevailed up until the end of the Cretaceous, 65 million years ago, when a big asteroid hit Earth and caused basically the extinction of everything but shrew-like mammals. And then today, if you want to look at the Ice Age, which ended 12,000 years ago, but it was, I guess it goes from 50,000 to 12,000 years ago. If you want to know how long that Ice Age lasted and humans were around, you basically, the age spans the amount of fingernail that you can remove with a single stroke of a file. So basically all our time on Earth as Homo sapiens is in that single stroke of a file. So here is a cartoon of what we think happened to make Cape Ann. As I said, continents were getting bigger, the land masses were getting bigger over time due to volcanism. And there was this supercontinent known as Gondwana, but there were also these microcontinents, which ended up drifting across what was then known as the Iapetus Ocean to dock with Laurentia, which is the rootstock of the North American continent. And they did it in sequence with the Merrimack, Neshoba, Avalon, and Maguma terrains. And we're the Avalon terrain. And so that can be seen all across the northeastern seaboard, but also in parts of Europe and the United Kingdom along some of the shorelines there. So I just find it neat to think that the granite that's in my house was made 450 million years ago as part of Africa, which ended up cleaving off to dock with the North American continent. So we're getting near the end. If you want to find out where the Avalon terrain exists, this is where it is in Massachusetts, followed by the Neshoba, Merrimack terrains. And west of this line, you go from what was in Gondwana into basically volcanic regions associated with Laurentia itself. So it's neat to think that Massachusetts embodies this history. All this time, 450 million years ago, life was well underway on Earth. As I said, you're already past the Cambrian explosion of life forms. And so the Earth has been a recipient of all kinds of chemical generosity, beginning in these star-forming nebulae, where the massive stars can reconfigure the molecules that are in the nebula. And that all can go into the formation of a forming star and planetary system. And that forms a new star with its planetary system. That star will evolve and outgas either placidly or violently, whatever it was able to make. And this stuff goes back into the interstellar medium and gets caught up in new clouds of star-forming gas. Earth has been the beneficiary of comets. We think that the water is not of cometary origin, it's more internal, and it was outgassed by the interior of the Earth. But the comets are an important deliverer of molecules, organic molecules, including ethane, acetonitrile. Amino acids, we know are in interplanetary space because we find them in the meteorites that have come to Earth. And these are basically the feedstock of proteins, which is a macromolecule. Other macromolecules that have been made here on Earth include RNA, DNA, the carbohydrates, and the lipids. So Earth has been a very favorable place for further molecular complexity. But where did the life actually begin? Was it down deep in the volcanic vents, which have heat for energy and what is this? And sulfur-based chemistries, or or is this not favored? It turns out that some people think that water, being surrounded by water, is not good for the hookups that are necessary to build these larger molecules. But at least nowadays, we can see that life is flourishing in these volcanic vents. Perhaps the life arose in very hot pools of acidic water, such as can be found in Yellowstone National Park. And these different colors represent different kinds of heat-loving microbes, which prefer a very specific temperature. These are known as thermophilic organisms. So is this where it happened? Or did it happen in a more temperate situation? Now, this is a quarry here on Cape Ann, so that's man-made. But the idea of a pond, a warm little pond like Darwin suggested, might be just the thing, especially if it can dry and wet, if it can go through cycles of drying and wetting, because that concentrates the ingredients so that they're more likely to hook up. An example of this is this scum, this dark scum on the shore, on the granite. It's made of fungus, but it's very salty because of the wetting and the drying. But even so, life was able to get a toehold here, well above the high tide line in the splash zone. And of course, we now can see life such as these barnacles that are clinging to this granite, and they are happily living with the tidal situation here on Earth, where the water comes and then the water goes. On land, there's the lichen, such as is on my house, and this is a symbiotic situation where you have photosynthesizing algae in concert with fungus, which is getting the nutrients. And these are very sturdy and hardy life forms. I've been disappointed that we haven't found anything like that on Mars, but maybe you need an atmosphere with enough oxygen. So the story does continue here on Cape Ann, where you live, and throughout the cosmos. We all have our to-do list, and the cosmos certainly does as well. And so I want to thank you for your kind attention, and may you enjoy clear starlit lights going forward. Thank you. Okay, let's stop the share and ask if you guys have any questions. Michael, are you going to
unmute myself.
Yeah.
Okay.
Roger that.
Nebulae. I have told people out in the field that a particular nebula was about as dense as vacuum. And so I was wondering if planetary nebulae and star-forming regions are equally dense or not dense, or if one is more dense than the other. Do we have that data?
That's a good question. And it can be answered because they have means of determining densities based on the spectral line emission from various atoms and ions. For example, the light from once ionized sulfur produces light. I just said light, but the light is at two different wavelengths, and they can look at the balance of intensities between those two wavelengths, and they can get a handle on the densities. So I'm not going to give you an answer. I can just say that it's possible that they have those densities determined.
Yeah, they have. They observe, let's say, molecular gas where stars form, and they can work out the densities in certain. I mean, the gas is very hierarchical in that it has structures within structures within structures, as you saw in the simulation that Bill showed.
Mm.
And you have densities on the outskirts of molecular clouds where stars form of like 100 to 1,000 molecules per cubic centimeter. And then when you get into these cores, you can have much higher, like 10 to the 5th, 10 to the 6th, much higher. And stars will form in cores that have these higher densities.
And then the subsequent evolution, which you were talking about, Michael, where maybe the natal gas and dust has all gone away, but then the star starts outgassing all by itself and produces those nebulae known as the planetary nebulae. Those have their own densities. And I can't give you the answer, but I think they're on the order of hundreds to thousands of particles per cubic centimeter. But I can't remember.
That's not a lot.
No, it's in the vacuum area.
So I wasn't lying. Good.
Yeah.
I'll accept that as a response.
Yeah, Bill?
Yes, Paul.
Yeah, I got a question that I've thought of. And it's not a specific question. 100 years ago, they thought the Milky Way was the universe. And then Hubble and his buddies started realizing things were expanding. And then they got into radio astronomy. Do you think 100 years from now, people will have a different view of the universe and its nature? You know, its size and so on.
That's a good question too, because right now there seems to be a consensus that the universe, our space-time started around 14 billion years ago. Will that change? I don't know. It would suggest that the expansion history of the universe, of galaxies, is much different than what we think it is. We basically think that it's been fairly steady with a slight acceleration. And so as far as the age of the universe is concerned, I'm predicting that it's probably going to be still 14 billion years ago. Am I happy about that? No, because I've always wanted a universe that was like about 20 to 30 billion years, so that there would be enough time for matter to get itself together to make the galaxies. But now the theorists have been able to figure that out as well, that the overdensities get denser and denser with enough time, in the amount of time that we think is left for that to occur. You know, it's only on the order of a few 100 million years now. So I have a subjective feel. I would rather have a much older universe, but everything seems to be pointing towards this 14 billion year old age.
The other thing is that we can only see so far out. And the argument is, well, we don't know what's on the other side of how far we can see out.
Right. There's a horizon to how far we can look.
Yeah.
Because as you look farther and farther away, you're looking back in time, because it takes a while for those photons to get to you. And at some point, we're looking back to the point where the universe hasn't been made yet.
Right.
So there's a horizon. And so this whole notion of multiverses,
Oh, yeah.
which suggests that there are many other space-times co-evolving with one another. All I can do is say that these notions exist and cosmologists are working on them.
Bill, the young age, it's better that way. We're still under warranty.
Touche. All right, after having this wonderful water, which got made God knows where.
I wanted to mention something. You were talking about how helium formed after the Big Bang. Yeah, you brought up an interesting point that I hadn't really thought about, is that you need neutrons, and you need the neutrons to not decay before the helium forms.
Mhm.
But the process, I think, is a little bit more complicated than you mentioned there. I'm sure aware of course, but the neutrons break down, but in the process, the neutrons will create more protons that they do in our atoms, the atoms of our bodies or whatever. But also because there are a lot of high energy electrons, which would also help combine with the protons to create neutrons. So,
Right.
so there'd
So
be
there
a
might be a little ecosystem for a few minutes.
sure, yeah, for a while before the density and the temperature of the universe got too low for that to happen. So,
Right.
yeah.
Yeah. It's a pretty successful, the hot Big Bang theory. And it was all put together by these guys uh, in the 50s, I think it was.
Something like that.
Yeah. Pretty impressive. They had to act, it actually ended up constraining the time for when everything had, for what is it, cosmo nu cosmic nucleosynthesis, I think is what it's called. Primordial nucleosynthesis.
Yeah.
Yeah. um, Pretty impressive. So at that, for me, I'm basically a cosmological tourist.
Well, they haven't shut the cosmos down for COVID yet, so you know.
No, they didn't shut the cosmos down. Yes, and there have been other events which uh, reminded me of that. That when 9/11 occurred, I was on my way from Rockport to Boston to teach at Tufts, and by the time I got there, the buildings had collapsed, and it was time to teach. And I asked the students, "What do you want me to do? Do you want to talk about what has just happened, or would you rather me talk about the universe?" And they said, well, "Why don't you just talk about the universe?" Um, I think in some ways it was reassuring for them that the cosmos
Yeah,
was just going
yeah.
on and on.
It's probably easier to deal with the universe than what was happening, I guess.
Yeah. So it's one reason to get into astronomy. There is a certain element of reassurance uh, that things go on. I see you, Laura. You going to ask a question?
I do have a question. It could be very ignorant, so please forgive me, but you had an interesting slide that showed our sun in relationship to the other stars, and then there was a line that was indicating the direction of the galactic center. And
Hmm.
I wondered if you could say something for a novice person like myself about how we know about that, like which way to go, and like
Which
this
way
is
to
the
go?
way to the galactic center.
Well, I have to admit that the amateurs had it right. All they had to do was look up, and you can see that
Huh.
there's something special happening in Sagittarius. That the band of the Milky Way gets thicker and brighter there, and it turns out that that's where the hub of the galaxy is. Um, we only see in about 5,000 light years. We don't actually see into the center, which is about 27,000 light years distant. Uh, but our view is still good enough to match with what was determined through great effort by basically looking at radio wave emission and noting that the velocities, the Doppler velocities, were going in one direction on one side of the center and going the other direction on the other side of the center. So
Yeah, the first detection of the galactic center itself was by Carl Jansky in the 1930s. He was a radio engineer working for Bell Labs, and he wasn't. No, there was no radio astronomy back then. He was just trying to find sources of noise with this large antenna, many meters in size.
hmm,
He was trying to find the noise from thunderstorms, but he found this strange source coming from the sky, and it didn't. Over the course of 24 hours, it wasn't exactly 24 hours. It was 23 hours 56 minutes. It was the sidereal rate. So he realized it was beyond the solar system, and further observations and afterwards, as Bill was talking about, confirmed that it was the center of our galaxy.
And that is contrary to what was thought by some leading astronomers who thought that the sun was the center of what was being called, I don't think it was called a galaxy yet. And that was based on counting stars and estimating their distances. And that led to an erroneous determination that we were in the center of it. Everything was it was denser towards us, and then it thinned out away from us. But that ended up being an artifact of erroneous distance measurements due to the obscuration by dust.
Oh.
And I'm drawing a blank. There was a name for that universe, the something universe. I'm drawing a blank. But so even the best astronomers doing the most sophisticated work can completely get it wrong.
Bite your tongue. No way.
Well, this has been great. I know I'm going way over time for 1623 Studios, so I'm probably going to have to pack it in. Christine, I'm glad you were able to make it throughout the whole thing. Oh, maybe not. So any other questions or comments before we call it quits?
Thanks, Bill. It was great.
Oh, okay. That's what I wanted. Thank you,
I'm
Chris.
here.
Okay. Thank you, everybody. It'll get on the Galactic Inquirer and also on 1623 Studios, our local cable station. Take care.
And YouTube as well, right?
And the YouTube channel, yes.
Yep.
Thank you, Phil. Take care. Bye-bye.
Bye.
Thanks, Bill.
Thanks, Bill.
Great. Great.
Thanks, Bill.